In this video, we will see how the power system can be represented in the per unit system that is widely used in the power system industry to express the values of voltages, currents, powers, and impedances of the various power equipments. The basic components of a power system are generators, transformers, transmission lines, and loads. The interconnection of the different components of the power system can be represented by a one-line diagram as shown in the figure. This figure shows the symbols are used to represent the typical components of the power system. This is a one-line diagram of the power system and it is consisting of two generating stations connected at bus A and bus B as shown in the figure, and the both are being connected through a transmission line. The advantage of one-line representation is its simplicity. One phase represents all the three phases of a balanced system. At bus A, three generators G1, G2 and G3 are connected and the connection is grounded star connection. At the bus A, the load is also shown connected. At the bus B, we can see the two generators G4 and G5 are connected with star connection grounded. Load is also connected at the bus B. Between bus A and the bus B, a transmission line has been connected through the transformers T1 and T2, and the connections of the transformer is delta star with the star grounded. All the equipment has been connected through the circuit breakers at both the ends. The one-line diagram may serve as a basis for circuit representation of the different components of power system. Here we are making the equivalent circuit of the components of the power system, and the representations is known as the impedance diagram or the reactance diagram. The reactance diagram will be drawn by neglecting the resistances. So here we can see the impedance diagram and the reactance diagram has been represented. There are certain assumptions that need to be followed while making the impedance diagram. Under balanced operating condition, the generators can be represented by a voltage source in series with the inductive reactance. For generators, the internal resistance is negligible as compared to reactance, and that's why in the diagram only the inductances has been shown connected in series with the generator, which is represented as a voltage source. The loads are shown by the impedance in figure A. The transformer core is ideal and it may be represented by a reactance or impedance referred to the appropriate side. The transmission line is converted by an equivalent circuit in form of medium length line and it can be denoted by a T circuit. Alternative representation, this pi circuit can also be applied. The delta Y connected transformer T1 may be replaced by an equivalent YY connected transformer so that the impedance diagram may be drawn on a per phase basis. For reactance diagram shown in the P, all the resistances are neglected. Static loads and the capacitance of the transmission lines are also neglected. Also, neutral grounding impedances do not appear in the diagram as balance conditions are assumed. The per unit value of any quantity is defined as the ratio of actual value to the chosen base value in the same unit. Computation of power system having two or more voltage levels becomes very complex and difficult when it is necessary to convert the currents to a different voltage level when they flow through a transformer. The other way of simplifying the analysis is with the help of the set of base values known as base quantities, and these base quantities they are assumed for each voltage level. To get the percent value of the quantity, we need to multiply the per unit value of that quantity by 100. The per unit and percent quantities and their bases exhibit the same relationships and they obey the laws such as Ohm's laws and Kirchhoff's law. A minimum of 4 base quantities is required to completely define a per unit system, and these are voltage, current, power, and impedance or admittance. If two of them are set arbitrarily, then the other two become fixed. For a power system analysis, all the impedances must be expressed in per unit on a common system base, and to accomplish this, an arbitrary base of apparent power is selected, for example 100 MVA, and then the voltage basis must be selected. Here base current is given as the ratio of base volt amperes which is chosen and the base voltage which is again chosen. So we have the base current, then we have the base impedance which is given as the ratio of base voltage to base current. Once the base values are calculated, the per unit values can be determined with the per unit voltage, per unit current and per unit impedances can be calculated. Where in the per unit representation, the numerator denotes the actual values and the denominator represents the base values. For example, per unit voltage will be written as actual voltage by the base voltage. Per unit current will be written as actual current by base current, and similarly the per unit impedance will be written as actual impedance by base impedance. To represent the quantities in per unit representation, first we will discuss about single phase system. We will be choosing any two quantities arbitrarily and that will be fixing the other two quantities. After doing this, we need to select the base volt amperes and the base voltage for the system in order to calculate the per unit quantities. For three-phase system, which is a practical power system, again we'll be choosing two quantities arbitrarily and that will be fixing the other two quantities. Then we need to select the base volt amperes, but because this is a three-phase system where usually the volt amperes are specified either in MVAs or in KVAs. If it is specified in MVA, then we need to select the three-phase base MVA and base KV, which is line-to-line voltage. If the volt amperes is specified in KVA, then we'll be choosing the base KVA and we'll be choosing the base voltage, which will be volts line-to-line voltage. After finding that, we can now calculate the base quantities for current and impedance, that is the base current and base impedance can be calculated as shown. So we can summarize the steps to make a per unit diagram, which can be obtained once we have the single line diagram of the system. So the step 1 is we need to select the common base MVA for the system. Once the base MVA has been identified, we need to divide the entire circuit or entire network or system into different sections, and that division can be done on the basis of the location of transformer. That we will discuss with the help of an example. So once the sections has been identified, we need to select the base kV for each of the section. Because the voltage, because the transformers are there, so voltages will be different at different point of the network. So we need to divide the network into different section, and then we need to select the base kV for any one of the section, and based on that, the voltage basis for the other section can be determined using the voltage ratio of the transformer. After doing all the steps, then we'll be calculating the per unit impedances. The per unit system gives us a clear idea of relative magnitudes of various quantities, that is voltage, current, power and impedance. The per unit values of all these quantities, impedance, voltage and current of a transformer, are same regardless of whether they are referred to the primary or the secondary side. So this is a great advantage since the different voltage levels disappear and the entire system will reduce to a system of simple impedances and per unit. So per unit quantities will remain same on either side of transformer independent of the voltage level. So this helps in analyzing the network very simplified way. Then the per unit systems are also ideal for computerized analysis and simulation of complex power systems. The impedance of individual generators and transformers as supplied by the manufacturer is in general based on the generator or the transformer ratings and usually expressed in terms of percentage or per unit quantities. The impedance of transmission line is usually expressed by their ohmic values. So all the impedances, they must be expressed in per unit on a common system base. That is, a common system base needs to be selected in order to carry out the analysis. So an arbitrary base for the apparent power can be selected and then the voltage basis must be selected. The remaining voltage basis can be determined by the various transformer turns ratios. That is, the per unit impedances needs to be referred now to a new voltage base, which is different from the one selected by the manufacturer. So to attempt that, we'll be using these formulas, that is the per unit impedance per unit old, that is the per unit impedance on the power base, old power base, and the voltage base old can be written as Z per unit old, and that is indicating the ratio of Z ohms and Z base old. So where the Z ohms indicates the actual impedance. So this can be converted into a new base once a common base has been selected for the entire system. Then this old base values can be converted to new values with the help of the formula Z per unit new. If the voltage bases are same, then the formula specified in the last line can be utilized. In this example, the one-line diagram of three-phase power system is shown, and now we'll be making the impedance diagram for this network. The system data is specified in this problem, and we can see here that the ratings of the generators, transformers, and the motor load has been specified with their reactances specified in percent. If it is specified in percent, we can write them in per unit as 18% for the generator G, we can write as 0.18 per unit. Now, in order to proceed for this question, first we need to divide the network into sections. So let's see how to do that. So let us now solve this question. So to start with, first we need to select a common base for the entire network, that is in MVA. So here we are selecting SB, that is the common base MVA equal to 100 MVA, and we have taken it 100 MVA, although we can take the other values as well, but it is preferable to take 100 MVA because the calculations will become easier than if we take in multiples of 100. So after selecting and after choosing the common base MVA of 100 MVA, the next step is we need to divide the entire network into sections. Now how to divide the network into sections is also on the basis of the location of the transformer. So first we will see in the network that where are the transformers located, and on the basis of location of the transformer we can divide the network into different sections. So here you can see that we have divided the network into 4 sections A, B, C and D on the basis of the location of the transformers. After dividing the network into section, the next step is we need to select the base kV in any one of the section. So here we are starting with the base kV. We are choosing from the section A, and we can choose any other section, but here we have selected the section A, and on the section A we know that generator is connected at the node 1, and the node 1, the voltage at the node 1 is specified as 22 kV. So it means the base voltage for the section A will be 22 kV, which we have written in the step 3, VB1 is equal to 22 kV. So we have chosen the base voltage at bus 1 equal to 22 kV. This will help us in fixing the voltage basis for the remaining buses, and that we will do in accordance with the transformer turns ratio or the voltage ratio of the transformer. So each of the section we can see we have defined the voltages at the different buses. For the section A, we have bus 1 located, so we have defined the voltage base as VB1. Similarly, for the section B, in which the bus 2 and bus 3 are lying, So we have designated the voltages of these buses as VB2 and VB3. For the section C, bus 4 is lying, so we have designated the voltage of this bus as VB4. And similarly, the bus 5 and 6, which is in the section D, the voltage has been defined as VB5 and VB6. Now we need to find the base voltages of all these buses. So that we will do in accordance with the transformer turns ratio. So here we can see that VB2 we need to find. So for that we are taking the ratio VB2 by VB1 equal to 22 by 220. Now this is the ratio which is already given for the transformer T1 in the data. So VB1 we have already determined, or we have already chosen VB1. So from this now we can calculate VB2. So after substituting the value of VB1, we can calculate now VB2 in accordance with the turns ratio or voltage ratio of the transformer, and this will give us VB2 equal to 220 kV. Now because between the bus 2 and bus 3 the line 1 is connected, and the line 1 is the voltage of this bus is 220 kV. So we know that the voltage of both the buses 2 and 3 will be same, that is VB2 will be equal to VB3, and that will be same as the voltage of the line 1. Or we can understand in this way also that the voltage, base voltage VB1, which is on the LV side of the transformer T1 is 220 kV, this we have chosen, and hence the base on the high voltage side can be determined with the help of the voltage ratio of the transformer, and that's why we found VB2 equal to 220 kV. Now once this 220 kV is calculated, this is also fixing the base of the HV side of T2 at VB3 equal to 220 kV, and on its LV side at VB4, so which will be evaluated in the same way depending upon what is the voltage ratio specified in the question. So we can evaluate VB4 also, and VB4 will be VB4 divided by VB3 equal to 11 by 220. So this will give us the VB4 equal to 11 kV. Similarly, we can evaluate the base voltage at the buses 5 and 6, keeping in mind the voltage ratio of the transformers in the particular sections. Now the step 5 is to convert all the impedances in per unit according to the voltage basis that we have evaluated in the step 4. Now first we'll be doing the calculation for the generators and transformers. That is, we are finding the per unit values for the generator and transformers. Now since generators and transformers are having the voltage bases are same as their rated values, so their per unit reactances on 100 MVA base can be calculated, and for that we can be utilizing this formula Z per unit new equal to Z per unit old, which is specified data for this particular component, multiplied by the S base new, that is MVA base new divided by MVA base old. For generator G, the manufacturer data sheet is specifying the reactance X as 18% and the MVA as 90 MVA. So utilizing this formula, we can calculate the impedance in per unit new for the generator as Z per unit old is equal to 18%. So we are writing here 0.18, and this will be multiplied by the S base new, which is chosen for this system, and we have chosen 100 MVA, so we are writing 100 divided by S base old, which is the MVA specified in the manufacturer data sheet for the generator, equal to 90 MVA. So when we solve this, we get 0.02 per unit. So this is the per unit new impedance for the generator on a common basis that has been selected. If we want to calculate the per unit values in percent, then we need to multiply the per unit values by 100, and that gives us 20% for the generator. Similarly, we can calculate for the transformer T1, T2, T3 and T4 using the same formula for the Z per unit new. So for the transformer, the reactance has been T1, reactance has been specified for the transformer T1 as 10%, and that needs to be multiplied by the S base new, which is 100 MVA, and divided by the base MVA old, which is specified for the transformer T1 as 50 MVA in the data sheet provided by the manufacturer. So this gives us 0.02 per unit. Similar way, we will be calculating for the other three transformers T2, T3 and T4 all the impedances in per unit. Now let us calculate the per unit impedance for motor which is connected at the bus 4, and we have already found out the base voltage at the bus 4 as 11 kV. Now the motor reactance is expressed on the data sheet provided by the manufacturer is 66.5 MVA and 10.45 kV. So we'll be utilizing the formula to calculate the per unit impedance for the motor as Z per unit equal to Z per unit old, which will be multiplied by the base values new, MVA base value new divided by MVA base old multiplied by V base old divided by V base new square. So on substituting all the values, we'll be able to get the per unit impedance for the motor as 0.25 per unit or 25%. Now, in order to calculate the impedances in per unit for the line 1 and 2, first we need to calculate the base values of the impedances for both the lines. And in order to calculate that, we'll be utilizing the formula Z base equal to VB square. VB square stands for the base voltage and that will be in the kV and line to line divided by the MVA base. So using this we can find the base impedance for line 1 as 220 square divided by 100, where 220 is the base voltage for the line 1 in kV, that is 220 kV. So we have written here 220 kV square by 100, which is the MVA base chosen for the system. So this is 484 ohms. Similarly, we can calculate for the line 2, and for the line 2 the base kV line to line is 110, so we'll be getting this as 121 ohms. After obtaining the values of the base impedances for the line 1 and 2, now we will be calculating the per unit impedances for these two lines using Z per unit equal to Z by ZB, where Z is, the meaning is Z actual value divided by the Z base value. This is equal to Z times the base value of the MVA divided by square of the base value of the voltage. So we can substitute for the two lines the desired values and we'll be able to get the per unit reactances for the lines or the per unit impedances for the line 1 and 2 as 0.1 per unit and 0.54 per unit. Now the calculations for load will be carried out, and for that again first we need to calculate the actual load impedance. So the actual load impedance will be calculated as the V line to line square divided by the conjugate of the apparent power of the load, because in the question the load apparent power at 0.6 power factor lagging is specified, and that we are writing as 57 angle cos inverse 0.6, right? So when we take the conjugate of this, we can write this as 10.45 kV square divided by 57, and the angle is cos inverse 0.6 gives us minus 53.13 degrees, and this gives us the two values on the two coordinates as 1.149 plus J 1.532 ohms. After calculating the actual impedance, which is actually also the phase value, we can say. So after calculating this, now we'll be calculating the base impedance and then we'll be evaluating the per unit impedance for the load. So to calculate base impedance, we can use the formula Z base for the load. This will be equal to the base value of the voltage for the load, that is 11 kV, because the load is connected on the bus 4, and for the bus 4 the voltage, base voltage has been taken as 11 kV. So we are writing here square of the 11 divided by the base MVA, that is 100. So this gives us 1.21 ohms. Now we can calculate the per unit impedance for the load. So per unit value will be the actual value by the base value, that is Z per unit old can be written as Z load, which is the actual value divided by the base impedance or the load, that is ZB load. So substituting the values, we'll get the per unit impedance for the load. Now we are able to obtain all the values of the per unit impedances of all the components which are connected in this network. Now after getting all the impedances, now we will be drawing the per unit impedance diagram for this system. So this is the equivalent per unit equivalent circuit for the given system, and here we can draw it like this. We can designate on this diagram all the impedances that we have derived. So starting with the generator, you can write the J.2, and then similarly you can indicate all the impedances for all the components that we have just evaluated. Between the node 1 and node 4, we have the components, that is the transformers and the transmission line, and similarly because it's a parallel lines are there, so we have on the line 2, which is there, the transformers and the impedance of the transmission line. To the node 4, we have two components are connected. One is the motor and another is the load, which is connected, and we have already obtained the per unit values of these. So we are just writing on the diagram the per unit values of the impedances. So this completes our complete equivalent circuit in the per unit representation for the given system.